got the semicircles, right? The area of the semicircle is pi over 2 times the radius squared. Now, the length of the radius is half of the diameter, right? That's a radius, right? The diameter is what is sitting on the plane. So the diameter is the F minus G, top minus bottom. Distance for the radius is half of F minus G. So we'll take that distance, F minus G over 2, sub it in for the radius. So the area of any one of those semicircles can be calculated by pi over 2 times the quantity, 1/2 of F minus G squared. So sub that in, we can simplify it. We'll square the half. We'll take all that out with a pi over 2. So our final integral looks like the integral from pi over 8, the integral from A to B, which 0 to the intersection of the quantity F minus G squared with respect to X, and then that constant out there on the front is what we pulled out. So there we go. Wait a second. In part 1, we did a rectangle there, and we still had that F minus G, the quantity squared, but there was a 1/2 out front. Interesting. All right, let's look at another one here. So same region. Hey, same region. This time, we're going to have squares pop out of the page at you, okay? So squares popping out. So drop the region flat, build the squares. There's my 3D representation there. So how do we find the volume? Well, we're going to start with the area of the cross section. And since that is a square, we just need side squared. Okay, well, what's the length of the side? The length of the side is the length of that distance between the function on top and the function on the bottom. Where have I heard that before? The side length is f of x minus g of x. That's all. The area of the square in terms of x is the quantity f of x minus g of x squared. Okay, we just pop that into the integral. So we integrate from 0 to 2.317, the integral from A to B there of just the quantity f of x minus g of x squared. Yet again, we see that same integrand with a different constant out front. Now, that's not a coincidence. It's just a lot of formulas for area involve multiplying some length by another length, or squaring one single length, like in a circle. So a lot of times you're going to have that length, f minus g or g minus f, or top minus bottom. You're going to see that in two different places. It's going to be multiplied by itself. That's not to say that that always happens, but you will see that a lot. You'll see that a lot. Again, don't think I've got to have f minus g squared. Don't think that. Think I'm going to start with the geometry formula and build from there. I'll build up to a definite integral. That's what you need to think. I'm going to give you a new region, I promise. Here we go. Let region S be the region in the fourth quadrant that's bounded by the x-axis, y-axis, and the curve 4x squared minus 3y equal to 12, which just ends up being some parabola. All right, so region S is the base of a solid, and this time we're going to build equilateral triangle cross sections, and we're going to cut them perpendicular to the y-axis. Okay, it's different. All the other ones have been perpendicular to x. I want to show you what happens when it's perpendicular to y. How do we come up with a volume? Well, if we slice perpendicular to the y, now we're talking about those thicknesses, the width of the slice, as a small change in y. So that means everything we come up with has to be in terms of y. So we'll take that region, drop it down flat, draw the equilateral triangles coming off of the page there. And then to calculate the volume, we'll figure out, well, the area of an equilateral triangle is √3/4 times side squared. Maybe you had to look that one up. I mean, I knew it. Maybe you knew it. Maybe you thought all triangles were just 1/2 base times height. Well, you're wrong. There's about 1,000 different area formulas for triangles, but for equilateral triangles, this is the one that you might want to remember. So the length of one of those sides in the equilateral triangle is just the distance, the horizontal distance between the parabola and the y-axis. So that's horizontal distance, that's right minus left. That's the function in terms of y minus the y-axis, which is just x equals 0. So manipulate that equation that we started with, solve that for x, so add 3y, divide by 4, take the square root of everything, understand that this is the positive square root in the fourth quadrant because it's positive x values. So we get that f of y is √3 plus 3/4 y. Okay, well, if that's the side length, then I'll pop that side length into the side length spot in the formula, simplify that puppy down to get √3/4 times the quantity 3 plus 3/4 y. Well, if that's the area of the slices, how do I find the volume of the whole thing? Well, I just need to integrate that area formula. And I'm going to do so on -4 to 0. Right, let me backtrack up to this region. Where does this region live? Once we determined it had to be in terms of y, we need to figure out the limits. Like, what are the limits of this region over here? Like, where does it live in terms of y? Well, it lives from the bottom, -4, to the top, 0. So the integral is going to be from -4 to 0. And then we'll integrate that formula that we came up with there, √3/4 multiplied by 3 plus 3/4 y dy. And then we're going to evaluate. You haven't seen me evaluate any of these because that's not the point. We can just use the calculator for that if we so desire. But it's the setups right now that you need to really focus on. So over these two parts, what have we learned? Well, we've learned that if we know what the shape has been built with a certain cross section in mind, we know that we can find the volume by just integrating the area of the cross section, like whatever that area is in terms of geometry, and that's what we want to integrate. So if it's a square, you're going to see side squared. If it's a semicircle, you're going to see pi r squared divided by 2 somewhere. If it's a star, if you could figure out the area of a star based on one of the side lengths, then go for it. Go for it. You could totally come up with any cross-sectional shape as long as you can put it somewhere in that region and figure out side lengths in terms of that region. Your imagination can just take off with the types of shapes that you can use. You're probably going to see top minus bottom as one of the lengths, or right minus left if you're in terms of y. Normally that pops up there, but it's all in turn. We've got to start with geometry, start with that geometry formula, build up to a definite integral. That's the best way to do it. Okay, next video, we're going to be spinning regions around. Oh, well, I'm dizzy just thinking about it.